me duelen las manos de estar en la computadora tanto.
Did you receive it? Hopefully everything runs okay today.
What's the point? Hey, that's the name of your first video, right?
You got it. Hey, you're in there. Huh? Okay.
I'm your biggest fan. I watched that video.
Yeah. Oh, you did watch that one?
It's the only one I watched.
Oh, you were the one who watched it. Okay, I see. I always wanted to know who was the guy who watched that, you know. Okay, so now I know. Okay. So it's 3, 2, 1, and we go online. Hello, everyone. How's everybody today? Hopefully as good as I am. I'm doing good today. Got my son on the other side as always.
Hi, guys.
So one of my sons. I got 3 sons. This is my the last one, the one I almost forget, you know, to have at the last moment. Today I want to cover a couple things. First, where we left off yesterday, Hans was discussing here the issue of turning theories into assumptions, and then you know, now the guy comes up with a theory based on that assumption. He comes up with a theory, and another fellow goes up there and uses that theory as an assumption, and so on.
I like to call them assumption chains.
Okay.
It's a chain of assumptions. It's
chains of assumptions.
The basic premise is I make an assumption and I make a theory based on that assumption. Someone else takes my theory on, let's say, magnetism to explain something else as his assumption and explains his theory with my theory in a way. And then somewhere down the line, someone's theory might be completely wrong just based on the fact that I messed up my assumption and everyone got that chain from me.
Yeah, and sometimes we lose track of where we got these original assumptions, right? And, okay, that's one issue I want to cover. The other one, I want to cover a couple issues that came up with both the monkey and Tom. You know, they raised a couple issues on what we were discussing. And then finally, I want to address today individual who I've contacted lately. I've been in... just starting a discussion with him. His name is Ivor or Ivor Cat. I don't know which is the correct pronunciation. I'll say Ivor. Sounds a lot like Igor, you know. Anyways, I want to address some of the issues because he raises some interesting issues. He talks about point, he talks about instant, and he talks about energy. And so I'd like to address a little bit about that, see if any of those have anything to do with physics, right? Okay, so let's go first with your chain of assumptions. What's the deal there? So you know, I can relate to that in this way, okay? Let me tell you where I relate to it. When I go back and I study light and I study gravity and so on, and I find some things, I say, where did he get this? Who was the starting point? You know, where was the starting point for this issue? And you go back in time, and it turns out that this guy used the other guy as a reference. And you go back to that reference, you know, and this guy used someone else as a reference. And so I kind of relate to what Hans is saying here, you know. You know, a lot of this started, again, in the 17th century. Keep this in mind. 17th century is known as the scientific revolution. You know, that's when science allegedly started, right? And why? Because they started doing experiments. And they did not trust Mr. Aristotle. They said, you know, whatever the Greeks did, that was all, you know, in their heads. That was just discussion. They never tested anything. They never put their theories to the test. They never experimented with their theories, okay? And specifically, you know, one of the famous issues out there is Galileo's allegedly rolling stones along inclined planes and possibly throwing stones from the Tower of Pisa, okay? And the issue there, he wanted to test Aristotle's assertion that heavier objects fall to the ground faster than lighter ones. You know, it sounds logical. You know, if you weigh like an elephant should fall to the ground faster than an ant. And it turns out that they fall at the same time. And that is spooky because
they hit the ground at the same time.
They hit the, yeah, what did I say?
They fall at the same time.
Okay, I meant the same thing. I guess. You're very specific.
You gotta be precise in this.
Okay, we got my son there being, you know, he's being too precise here.
That's my job. There's no such thing as too precise in science.
Anyways, the point is that if you throw an elephant and an ant, they both hit the ground at the same time, or should at least. And the question is, that sounds so counterintuitive. I thought this bigger animal, this bigger weight, this bigger mass should hit the ground faster. And, you know, allegedly Galileo either threw rolling balls on inclined planes or throwing stones from Pisa. There's different versions here. And he came up with, a counter argument. Says, you know, Aristotle is simply wrong. You know, he never tested his theory. And, you know, throughout those years in the early 1600s, throughout the 1600s, you know, 17th century, a lot of people, Robert Boyle, Newton, Huygens, they all did experiments in their own little dark basements. And they started overthrowing a lot of the notions they picked up from tradition. And so that's when the scientific revolution really kind of got a start, okay? And so since then we had something else, which is not physics, it's mathematics. We had all these mathematicians saying, okay, now we're going to do everything with equations. We're going to run an experiment, we're going to measure, we're going to put it into a nice little neat equation, we're going to call those equations laws. And you know, now that you have a law, you have to respect the law, whether you like it or not, because it's God's law. Okay? And I'm saying none of that has anything to do with science, let alone physics. Mathematics is not the language of physics. Science does not use mathematics at all. And you're saying, Bill, you're crazy. You're out of your mind. Yeah, I know I'm out of my mind. Let me tell you why. Not why I'm out of my mind. I can't explain that. Why are you out of your mind? We'll let the psychologists explain that one. No, I'll explain why science has nothing to do with math, physics has nothing to do with math, and math has nothing to do with physics.
Well, we've done that a million times.
Well, I'm going to do it one more time.
I wanted to go more specifically into the assumption chains. You're going back to what we talked about.
Okay, let me just cover this and then we'll go right back to the assumption chain. Let me tell you why. Just very briefly. Science, rational explanations. Math can only describe. And we covered that in the last couple of weeks. And so if math can only describe and science is about explaining, then clearly math not only is not the language of physics or science, physics being a branch of science, but it has nothing to do with science. In physics, we have to explain, I always use my little magnets here. Physics, we have to explain how these magnets attract. What causes this effect? I need no mathematics to explain to a little boy, you know, how that happens. Give me a little piece of paper so we can do the...
You don't have the piece of paper?
Yeah, yes we do. Somewhere we do. Okay, here we have a little piece of paper. We did this dangerous experiment yesterday. It's a billion...
hold on, get your science goggles on.
Yeah. This is a very dangerous experiment. It's been done many times, but only in the presence of rational scientists such as, you know, relativists and quantum mechanics. And that's this. Here it goes, okay? Watch it carefully. Okay, did you see any physical object hitting the paper? Why did the paper move? Was it spirits? Was it energy?
Or more specifically, do we need math to explain
Do we need math to explain this? No. If
Does math even help?
Yeah, I think it hinders, but
that's more to the point. Does math help at all to know exactly how much speed the paper moved or how much energy came out of your mouth? None of that helps me understand what the actual mechanism, what the domino effect of was there that resulted in moving the paper.
Because I don't need any quantities or equations to explain that to a 10-year-old. I say, look, there's this body of gas we call air. It's made out of molecules. It's made out of atoms. You can say, look, it's just a bunch of particles. Fine, I don't care. And that's what but I don't see any particles. All I see is you going and the paper moving from, action at a distance. And you say, how did that happen? That's magic, because I didn't see anything in between there. And all you have to do is say, look, you can't see the air. Oh, okay. Now I understand it perfectly. Assuming we have a bunch of particles, assuming we have, atoms, molecules, then we can understand the mechanism. And I always give another example just in case. And that relates to gravity. You see a farmer in the distance. And he's tugging, he's going like this, right? And on the other side, you see a donkey going, sticking his neck out, being pulled. How did he do that? I don't see anything in between them.
He's too far to see the rope.
I'll make it even better. You get closer and closer and closer, and you don't see absolutely anything. The guy keeps doing like this and pulling on the donkey from afar. And you say, how did you do that? Did you use magic? Did you use energy? Did you use force? Did you use mass?
He's got a fishing line.
And he says, no, I used a rope. What do you mean a rope? I don't see anything. Oh, I see why you can't see the rope. It's ultraviolet. It's got an ultraviolet color to it. So it's beyond our visible range. Okay, once you understand that, you say, okay, it's kid stuff. He was pulling on a donkey with a rope. I just couldn't see it, and I thought it was magic. But once he explains it and says, look, there is a rope there, you just can't see it, then everything falls in place. And so we don't need any math, we don't need any mass, we don't need any energy, we don't need any force, we don't need any time to explain how the farmer pulled on the donkey. We need a rope, we need a physical object, a physical mediator. And that's what physics is about, explaining how these things happen, how a magnet attracts another, what is the mechanism that compels a spoon to fall to the floor, not to the ceiling. That's physics, not all this mathematical nonsense that we see out there. Getting back now to your thing.
Yeah, just now you mentioned time, which is a perfect segue, a perfect example of assumption chain.
Okay.
But before I get to that, I just thought these assumption chains are really deep because they go all the way to the dawn of human sentience.
Yeah,
everyone just builds
at least 4,000 years ago when they started looking at these things, when we kind of gained a conscience.
In everything.
Okay.
Everyone builds on past knowledge.
Well, Newton said, I stand on the shoulders of giants.
What is that? That's really important to know. Why do we even read history and stuff?
Yeah, why don't we?
Yeah, why do you?
I like history. My son doesn't like history. I tell him he's got to read history so he doesn't repeat the same mistakes. But, I'm talking to the wind.
Everything we know today, we didn't just come up with it out of nowhere. We got it from our previous generation. They got it from the previous generation. They got it from the previous generation.
We memorize. We learn by rote.
It's that, but we take what they give us and then we build upon it.
Hold it, but we take it on face.
Some of it. Yeah.
Yeah, but we don't question it because we don't pass the test otherwise. No, because we don't pass the test.
It's not specifically about school.
Then what is it about?
It's about everything that you know. Everything that you know was taught to you.
Let's stop there.
Yeah.
Everything you know. You go to the high school.
Forget school.
Hold it.
Let's do it in the kitchen.
Where do you get your knowledge? You get it from school
in the kitchen. How to eat. How do you
you learn that when you're a baby?
Yeah, how do you use the utensils, for example?
Okay.
You're taught. Now forget school because that convolutes the issue. If you just have utensils,
but isn't that a school? Mommy tells you
that's a type of school, but that's but when we say school, it's confusing because now we're talking about actual teachers, and it changes the issue.
Your mommy is
I'm just trying to say that everything that we know, we got it from past generations. So in a sense, everything is an assumption chain of theory, assumption, where you kind of build on what you were given, and it's hard to know whether what you were given was the correct. I mean, this is also talking more about philosophy, how to live.
Yeah.
Like what's the best way to live? That's also different than what is physics.
Yeah.
In that sense, that is different.
What exists?
But in a sense, they both stem. Everything that you assume today, when you want to brainstorm for why does magnetism work, right?
Yeah.
You have a very narrow pool of theories to work with. You don't have 100 theories.
No. You're right about that.
Because
maybe there's no more than 10, I would say.
Because there are, from the pool of assumption chains that you were kind of raised with, or that you just saw in your day-to-day, things that you kind of intuit, you kind of build this pool of assumptions, and they're kind of implicit assumptions, going back to time, where you were trying to figure things out like the speed of light or gravity, and time kept coming up. And then only when you disregarded time as a faulty assumption did it make sense.
Yeah, because now you look at physics.
But that's why these assumption chains are very important.
Time got in the way.
It's important to keep in perspective that all our assumptions aren't just falling from the sky. That when someone makes a pool of assumptions to then build upon his theory, there's a whole history behind the assumptions people make. So when someone's, for example, you have this problem very often where they say, "Oh, there doesn't have to be a mediator between two objects for gravity." Like it just happens. Forget it. Like how does
magic?
There doesn't have to be a rope or a bead or whatever. It just happens. Gravity just happens. So they have this pool of assumptions that they just kind of take for granted. It's that taking for granted part that kind of irks me, because that's also where teaching goes south. When you try to teach me something and there are implicit assumptions or biases that you have that I don't have, it's very hard to teach. It's hard. You can't skip that. You can't skip that step.
You got to cover that.
Yeah, you got to cover that step. I got to be on the same page. Yeah. You can't start teaching calculus if I don't even know how to add, kind of thing. You know?
Yeah, you got to go in steps.
You got to go in steps. So there are certain. I mean, this is the biggest problem that you have when you're trying to get people to understand. Forget confronting or anything. Just trying to get someone to understand one theory. You have to kind of bombard them with so many assumptions that they don't already hold, that it takes years for them to finally get that moment, like, oh, now I get why Bill uses object, shape as object, location is this.
Yeah, because it all is comprehensive.
But it's like this web that you can't just take one definition out of context and take it on for it to make sense. You have to take the whole thing, and for that, it's...
Let me ask you something. Come over here. I want you to show your face here. I'm not talking to God, just in case. You know, we have my youngest son here. He's he's the guy on the other side. Okay, just
hey guys.
Just so you know that I'm not talking to the wind here. You know,
yeah, it's a recording.
It's kind of scary, you know, when you hear this voice out there in the wilderness. Okay, so
I'm just trying to show the importance of assumptions. Of the origin of assumptions.
Yeah, sometimes, you know, and that is true. You know, sometimes you take some things at face value. But what do we mean by that? You're taking face value means that you accepted or you believed. You know, because you're going to use in your theory, you believe the assumption, or the theory of someone else. Someone else had an assumption. He came up with a theory. You take the theory, his conclusions, his results, and you say, well, I'm going to accept them as a fact. And I'm going to use them as my starting point. That's going to be now my foundation. And now I'm going to build upon it. You know, like Newton said, you know, I stand on the shoulders of giants. And so now you build upon it. But it turns out we do this over and over from generation to generation. And at some point, you know, there's a generation out there, us maybe, you know, we're 400 years later from Newton and some of the Galileo and all these people. And we say, where all this come from? where did we get the wave? You know, I looked up the wave, you know, a long time ago now. And, you know, I said, okay, 19th century, this was famous. You know, everybody just believed in the wave version of light. And it turns out that if you take it before the 19th century, before 1800s, it was Newton who roared the particle. And by particle, they meant corpuscle. Little dot, little ball, tiny ball. That's what they meant by particle. That's important. And so they dealt with a particle for 100 plus years. Then 19th century, they went into the wave. You know, you had started really early at the century with Thomas Young. And he did his slit experiment. He said this can only be explained with waves. Then we had Fresnel, Augustin Fresnel, a French guy, and he came up and he looked at polarization. He looked at also the slit experiment. He explained it in terms of waves. He kept going with Faraday and eventually with, you know, people like Maxwell and Hertz and so on. And they all said, you know, light is some kind of wave. Transverse wave, to be more precise. They abandoned Huygens, Christian Huygens. He was a guy from Netherlands and also contemporary of Newton, and they abandoned his notion of a wave, where he explained water waves. He says, you know, you have a point source that explodes and turns into all these little vibrations. And each one is a point source of secondary waves, and so on down the line. And they said, well, you know, why light does not really work that way. It's more like a transverse wave, and that's what James Maxwell described, okay, mathematically. Well, that lasted until the 19th century when we had Mr. Planck, Max Planck. He came up and he said, you know, when I do the black body radiation experiment, you know, I have to consider that light comes in discrete packets, in discrete packages. And people say, how can that possibly be? Light is continuous. Well, he said, yeah, I think so, because remember, Max Planck did not believe in his own theory. He said, you know, this is what I present. This is the math behind it that describes it. But I don't accept the physical interpretation that, you know, light comes in discrete packages. Well, that's when, you know, by the time they got to the Solvay Conference, 5th Solvay Conference in 1927, they finally said, look, you guys believe in the wave, we believe in the particle, let's do something. Let's reach a consensus, let's shake hands, and we'll make it a wave particle. Particle wave, wave packet, whatever you want to call it. We'll merge them both together. And you know, Mr. Niels Bohr says, I'll come with a complementarity principle, which means that for these experiments, you can use the wave. And for these others, you can use the particle. Whenever you can't explain it with particles, just use the wave. Whenever you can't explain it with waves, use the particle, and so on.
That's like if at a soccer game, we have two referees, one referee for your team, one referee for my team.
Yeah, you can't explain it, so you reach a consensus. Well, science doesn't work by consensus. Unfortunately, science doesn't work by consensus.
I mean, I don't care about science, but Mother Nature sure does.
I hope Mother Nature doesn't say, well, you know, I think I'm going to convert the particle into the corpuscle into a wave just to explain the slit experiment, and then I got to convert it back to a particle to explain.
She changes it just to mess with us.
Compton's experiment, and now I got to change it back to a wave to explain, you know, I don't know, or to a particle to explain the photoelectric effect, and then back to the wave to explain polarization. Mother Nature, you drive her nuts if she could convert, you know, particles into waves. And then when you look up the particle, it's not the corpuscle that Newton talked about. Corpuscle is the particle is really a well, no, it's a field. Yeah, it's a field. And what is a field? You look up the word field, and it's an undefined word. There's all the words in mathematics. They're all undefined when they relate to, you know, when they try to give physical interpretations. And the most important word that's undefined is the word field. It's just you can think of it as a spider's web that extends throughout the universe. That's a field.
Theoretical.
But think of it in 3 dimensions. I'm not like a flat, you know, 2-dimensional spider's web, but think of it in 3 dimensions, radially. And a 3-dimensional spider's web goes to the edge of space-time, I guess. I don't know. So it's a bunch of values that surround an object. That's all it is. Whether you're talking about gravity, you're talking about the field for an electron, whether you're talking about the field of a pion, of a muon, it doesn't matter. It's a radially a radial region of values, of magnitudes, of units. That's what it's a mathematical concept. So you say, hold it. You're saying that this field went through the slit? How did it get all these, these spider web, the entire web through the little slit? And so
where does the particle start?
Yeah,
and so end? And all
it doesn't end in a rational physical interpretation. They convert the particle into a field, and they say that's what went through the slit. You say that doesn't make any sense. Of course it doesn't. We don't understand quantum mechanics. That's the answer they give you.
Well, that's what we ended up with the faulty assumption chains. So what we're kind of saying is kind of to question everything, question your assumptions. I mean, a good point to make is that what we believe are basically assumptions that we take for granted. Yeah. Any implicit assumptions that you make, we're going to call those beliefs. At least I'm going to call that belief. Belief, to me, the definition of belief is an assumption that you take for granted, that you don't... No,
hold it. Let's clarify that.
Explicitly make.
An assumption is what you take for granted. Belief means that you actually turn it into a fact. Belief means now you're going to believe it.
It's not your saying when you give a presentation. Right?
Yeah, okay.
All the assumptions that you make without stating them as such. For example,
then it's a fact. But then it's a fact.
Yeah, but it's really a belief.
Yeah, but what does a belief mean?
Let's go slow.
Yeah.
If someone gives a presentation and they explain magnetism, why these two magnets attract each other.
Yeah.
He's doing it on Earth. He's trying to explain an observation that he did on Earth, right?
Here it is.
Do it right there. There's gravity on Earth.
Yeah.
It has nothing to do with the explanation, but it might. So he's not invoking gravity per se to explain it. But he is implicitly. There is gravity in the gravity could have something to do with it. Let's put it that way.
Okay, it could. Yeah.
So it's in a gravitational field. We're trying to explain magnetism. I mean, as far as common sense goes, gravity has nothing to do with it. But all I'm trying to say is that he's implicitly invoking gravity. So gravity is more like a belief. It's like we don't have to talk about that. Everything that he doesn't explicitly state, okay, we're going to assume I have two pieces of metal. We're going to assume they pull each other. You just do all the assumptions. But there's a shitload of assumptions that you make that you don't state out loud. Like the color of the magnets.
Yeah, maybe not gravity, but you might make some other assumptions.
And those are kind of like, it's kind of in the realm of beliefs. Where it's like
you take for granted some things like, oh, you know, right?
Yeah, it's like, that's what I'm talking about. It's like, oh, that's a belief you have that I don't, so you do have to explicitly state that.
Until someone challenges you, and now you have to explain. What do you mean? You didn't go to high school? You didn't go to college? Exactly. No, I didn't. Please explain.
Please explain, exactly. If two mathematicians...
The answer is, no, I haven't. Please explain.
If two mathematical physicists were to explain, or one were to explain something to the other, they both had the same background.
Or
so there's a list of things of assumptions that they wouldn't have to explicitly state because they both got that in physics 101, 102, 201 and all that. It's like there's a lot of things that they can do shorthand with.
Yeah.
And those are more like beliefs. Like, okay, we're both on the same page on that. Let's try to build upon that.
A very case in point, time dilation. And you say, what do you mean time dilation? We can't dilate time. Time is not a physical object. Well, you don't understand the term time dilation. That means something else. And it's a code. You know, within the mathematical community, they say time dilation. And that's a shorthand for a whole bunch of other stuff that has nothing to do with bending time. You know, what do? You bend a second, you bend a minute, you bend a year. What is it that you bend over there at the mathematical club? And they say, well, you don't understand. You haven't taken mathematics, 202 or 101 or 302 or whatever. You haven't taken advanced mathematics. That's why you don't understand, because time dilation is something else.
You're not on the same page.
Right. And so the issue is they use all these code words, these code phrases. We transfer energy. We move the mass.
The problem with that is...
We carry the force. And they understand it, and you say, well, hold it. What do you mean you carry the force? You move the mass, you transfer the energy.
The problem with that is there is the implicit assumption problem, where since they both believe they don't have to explain that to each other, they don't visit the topic, so it stays underground. It stays all the problems with it.
Yeah.
All the unspoken variables. Yeah, all the hidden problems with an assumption kind of go unpunished.
Yeah.
Because they both kind of go you know what I mean?
Wink, wink.
Yeah,
nudge, nudge.
I mean, it's not wink, wink, nudge, nudge, because it's kind of like, okay, we both took that class, we don't have to talk about it, let's just build upon it, even though we don't really understand it. If some third person came in, some layman, and asked, hey, what do you mean time dilation? And then he starts asking all the quote-unquote dumb questions, and then they start rolling their eyes like, oh man, you just have to roll over these questions. Don't look at the details.
Yeah, don't take them literally.
Yeah, don't take them literally.
Yeah, you're not supposed to take them literally.
It's like they want the implicit assumptions that hurt to stay implicit.
Yeah.
They don't want to make those explicit because now you got to actually look at them.
So what do we conclude as far as assumptions then?
About that, an interesting conclusion or a question more that I wanted to ask is, because the moral that we're kind of going around is to question your assumptions, to question your beliefs, question, for example,
more than your theories.
Just question, like just whenever you're thinking about time, question, okay, what is time? You know, go into that.
And especially, let me clarify, especially when you don't understand. I mean, you don't just nod. You say, look, excuse me. You know, could you clarify that?
Or just to yourself.
I'm too stupid to understand this.
Or just,
could you clarify?
I'm talking more to myself. Like if I'm just in a room by myself, I'm trying to figure something out.
Yeah.
Then you're kind of forced to look at the implicit assumptions, because there's some assumption that you have that's not making that isn't right.
Because you don't understand the theory, because you didn't understand the assumptions to start out.
Exactly. So the pieces don't fit, so some pieces off. Which one is it? Then you go one by one. But then the question becomes, which is a very deep question, and you can't underestimate it because it's one of the fundamental questions, which is, where do you draw the line on what to question?
Yeah. And
for example, you don't question that there has to be a mediator between two objects to explain action at a distance.
I know, but a lot of people do. And it blows my mind when people say, why do you need a mediator? And I'm saying, you mean this particle affects this one at a distance, gravitationally, electromagnetically, any way you want. And you're saying this one affects this one at a distance. They call it entanglement in quantum. And there's no physical mediator? What do we do with them? With spirits? I mean, what are we going to introduce in that space? Think about that.
But then the question that you didn't answer yet, or just for anyone listening, is where do you draw the line on what to question? Because you do question some things.
Well, I think some things are more than common sense. I would put them above commonsensical. It's like, I don't have a word to describe it. It's like you're born with it. It's like no one had to teach me in my entire life. I didn't have to go to school for this. Yeah, I was born with it. I can say that between two parts, if this particle affects that one, if the farmer pulls on the donkey, if the magnet pulls on the magnet, there's some physical mediator in there. It's like, you know, for me, it's a non-issue. And there are people who say, well, why do you need a mediator? Why do you need to put an object in there? And it just blows my mind. So what are you doing physics with? How do you think a magnet pulls on another? With magic? With spirits? God? What are you going to put in between two magnets?
Just nothing.
Nothing?
We're just going to keep it unanswered.
I mean, you know, here we have, this guy pulls on that one. I can't even break them apart. You know, it's like, and there it sticks. Yeah. And it does it from, I can already feel it pulling here, you know, and, you know, here I'm trying to put them together, and I can't. They just go past each other.
But that's why the question.
And I'm saying, hold it, there's nothing in between there?
But that's why.
What is it, spirits, God, angels? What are we going to put in there? Energy, mass, what do you want to put in there?
But that's why the question is, everyone, is where do you draw the line on what to question? Because you do question some things. But there are some beliefs or assumptions that you kind of say, okay, I'm not going to touch these. Yeah,
but you know what I do? What I do is divide people into scientists, rational people, and irrational religious people. And I'm saying it's a religious person who believes that two magnets are attracted to each other or repulse each other without a physical mediator. These people simply weren't born with common sense.
Yeah, but that's just that one. For example, time, at some point, you were actually debating in your head. So you had the time assumption.
Yeah.
So you'd say you were back then. You were
well because I was brainwashed to talk about time. So I said, okay, all these equations have mass, they have time, and that's what I looked at. I looked at the equations, and I said, okay, here's time, here's mass, and that was just a stumbling block. But at the moment, I didn't realize that. I said, okay, this guy did this with time, like. Take just Newton's simple force equals mass times acceleration. You look at acceleration, it's got time in there. Meters per second squared. And you
seconds.
say...
You got seconds.
Yeah, you got seconds, you got time. So it was like I took it for granted. I said, okay, you got time in there. You need to include time. And it turns out that that's a description of what's happening. Obviously, you can't say that the car ran because time had something to do with it. Time was not a factor in pushing the car forward. If I have to explain the mechanism, the cause, I don't need time at all.
That gets weird.
Yeah, it does get weird.
Deep into that
no,
now.
Obviously not. But what I'm saying is that's when you start saying, well, I don't need time, I don't need mass. I don't need energy, I don't need any of those words invented by mathematical physics. What I need to know is what physical objects are involved in pushing that car forward. If someone tells you, look, I'm a technician, mechanic, you go to take your car to the mechanic and say, how does a car work? Do you think this mechanic is going to say, well, let me talk to you about energy and force and mass and time? No. He's going to say, look, the gas comes out of here, goes through this tube, comes to the engine. He's going to talk about objects. He's going to talk about physical entities. And again, how did that happen? Did it happen through energy, mass? What was it? No, it was air that I blew against. In other words, all the things involved are objects. And I can make a movie of my theory. I just have to make the air visible. That's all. Once I make it visible, it's for kindergartners. You blew something invisible, which are all these particles. You blew against the paper, and the paper moved. Very simple. It's like the wind blows the trees down, or the house down, hurricane. We all understand that. We don't need any math, any fancy words, concepts such as energy, force, and mass to explain that.
So going to the title of the video about points. The word point used in science. I get this feeling that you're going to talk about the faulty assumption that they're making.
Yeah, here we're dealing with assumptions. We have this individual. His name is Ivor Cat. I believe I'm pronouncing his name correct.
He's on court?
Correctly. No, he came through a friend of mine. And we started just discussing just couple days ago, so I don't know him well, and I don't know all the things he's got coming. I just presented my version of physics. I said, look, the golden principle of physics is physics requires an object. You can't do physics without an object, yes or no? And an object is that which has shape, yes or no? He didn't answer that question, but he had an earlier answer to these questions where he says the following. He says, where is it here? He starts out with this. He says, I start with primitives or a primitive. What is a primitive? It's an undefined word. That's what it is. That's what primitive means. It means you can't define it in more fundamental words because those words require definitions as well and so on down the line forever. So they call those primitives, and what they do, what the mathematicians do, is simply get around from defining the key word they have to define. I need a definition for the word point, and they'll never define it.
To clarify that, for example, the word motion would be an example of a primitive. Because
I can claim anything as a primitive. I can say energy is a primitive.
But what they're essentially saying is there are certain words that you can't define because
it would destroy their theories. That's the way I look at it.
Like, they can't define the word motion or location because
why not?
It requires other words to define them, and then you go off on a tangent of that has nothing to do with science or something like that.
Yeah,
I kind of get the notion that they're going for, but it's still not. I wouldn't call it science.
What they're doing is avoiding a definition. That's what they're doing. They're avoiding because they don't want to do grammar. They want to do math. They want to do equations. And I'm saying equations have nothing to do with physics.
Yeah, because
so you can't bring equations in there, which we need to explain how a magnet attracts another. I need no math to do this.
Yeah, the issue with primitives is I think that just shows the level of kind of what do you call it? Avoidance that
it's avoidance.
Not even avoidance. It's underestimating. That's what I'd say.
Underestimate.
They underestimate words and definitions.
Yeah,
It's not held on a pedestal as it should be in science.
Yeah.
It's underestimated. It's not. It's kind of like we're gonna operate on a human body, but we're not gonna use something that's like IVs or something.
And let me tell you why. Let me tell you why it's developed that way. The way it developed is that from the days of Newton, what they've done is they believe at all times that math is the language of physics, and that science requires math. That's where it all starts. And so they always were looking for these laws of God, I guess you could call them, the laws of the universe, where they say, look, we can explain everything with equations. But it turns out that math cannot explain. And, you know, we had the statements. Let's see if I can find it here. Do I still have it? I don't know if I have it. Is this it? Maybe? No. Well, okay. I lost it somewhere. But we had yesterday and the day before, we had Nobel Prize winner Steven Weinberg. We had Professor Donald Simonek from Pennsylvania University, Lock Haven University. He's an emeritus professor. They both said the same thing. Science doesn't explain. Science describes. Why? Because math describes. So they equated science, meaning physics, with math. And so they say, you know, you need math for physics. That's why, because that's what they do. They do equations. We don't need math for physics. I need to explain how a magnet attracts another. I need to explain why a pen falls to the floor and not to the ceiling. That's what I need to explain.
What was the where did the argument start with this Ivor?
Well, more or less here. You know, essentially,
what were you trying to get to the bottom of?
I'm trying to get to the foundations of physics. What is physics about? That's essentially what I'm talking about. What is, because we don't seem to agree or be on the same page as far as what physics is concerned. So he gives me an idea here. He says, I start with primitives, right? Okay. And by that he means primitive means undefined words. So he starts with undefined words. That's what primitive means. Means that he can't define his own terminology. Okay, fine. So we go to the next step, and it says, at a point. Okay, he's going to bring Euclid's point here. That's essentially what he's talking about. There is no knowledge about the rest of the universe at that instant. Well, instant or a point? Is point an instant? Instant is a point. Point is location. Location is point. Point is a number. Number is a point. What are we talking about when we say point? Well, obviously, it's a primitive word because they don't want to define it. If you define it as a dot, which is what they put on the board, objectively, that's what a point is, a dot. And you say, what are you going to do with that dot? It's a two-dimensional dot. And they say, no, it's a zero-dimensional. What do you mean zero-dimensional? I see two dimensions. The dot, all dots have two dimensions, a minimum. Maybe they have three, but for sure they have two. And they say, no, no, look, you're mistaken. See, it's how we locate the point. And we need zero dimensions to locate a point because it's where it's at. And okay, and you need two coordinates then to describe a plane, one coordinate to describe a line, and so on. It has nothing to do with physics. None of that has, all that geometry garbage invented by Euclid has nothing to do with physics.
What was he trying to explain?
Well, I don't know. For example. Well, let's get to the following. It says, there is no knowledge about the rest of the universe at that instant. So a point is an instant, which is who knows what else. It's an undefined word. There might reside something. Something, whatever something is, because that's the word I'm trying to get to, the word something. At that point, there is something at that point. Now he treats it as a location, not as an instant. And there may be something arriving at that point, at that instant. So,
what is he saying?
Yeah, I know. We're having something, which is the word we're trying to get to, and he doesn't pay attention to this. He said, well, we don't care about what something is. We're just saying something arrives at that point. He's worried about location. He's worried about instant. He's worried about, for sure, numbers. But he's not worried about what the object looks like. Is it an elephant? Is it an ant? He says, we don't care. Why don't you care? Don't you care in physics whether it's an elephant or an ant? He said, no, because we're going to treat it mathematically. We're going to say that something, whatever that something is, arrived at that point, at a given point in time, instant, and that's all we care about. We care about the action, not about the actor. Okay? And he continues, I'm familiar with EXH, energy, current traveling at sea, velocity of light, right? Some of which may pass through that point.
Through the point?
Yeah, so he's got energy passing through that point, but he says it has energy density, not energy. So, you know, he's
energy density, not energy. See, when you read these things, there are so many things that, I mean, okay, yes, but he's not explaining anything because he's using words that he understands. Let's give him the benefit of the doubt.
Yeah, okay.
Let's give him the benefit of the doubt and say, okay, he understands the theory perfectly, and it makes sense to him, and it's exactly how Mother Nature does it, right? Let's go the full mile. But that doesn't.
What did I do? Did I do something? Ah! I turned something off.
No, we're good.
You're good? I don't think so. Give it.
Yeah, we're fine. We're fine.
You're fine. I don't know why.
Don't make me nervous, folks.
I'm nervous now because I don't know why I can't see myself. Okay, fine.
So we're gonna grant him the benefit of the doubt.
Okay.
He knows what he's talking about, and it's exactly how Mother Nature runs her shop. That's exactly how the universe works. Okay. What he used there with energy density and energy, whatever that means.
Yeah.
But that's the problem. If he wants to explain that to me.
Yeah, how does he?
I don't know what he's saying.
He's saying you gotta go to college.
Assuming it's the gospel truth, and it like he just happened to stumble on the way the universe works, and it makes sense in his mind. It doesn't help anyone if he uses vague terminology that I can't then adopt.
But then he says that you got to go to college to get a master's degree in mathematics or whatever he studied in order to understand his language.
But then what's the point of even opening his mouth in the first place?
No, but this
this goes
back to what we said yesterday. This goes back to what we said yesterday. It goes to this. There are different levels.
Okay.
Okay.
Oh, I see what you mean.
So we have the kindergarten level, we have the high school, we have the elementary school, we have the college level.
He'll explain it up to the level.
Yeah, and so he says, "Look, I'm talking a college level here, but you're still in kindergarten, so you don't understand all my terminology." And so I say, "Okay, fine. Let's assume we don't understand his terminology. Let's start from scratch. Start with kindergarten." I mean, what did Einstein say? If you can't explain it to a barmaid, you don't understand it well now. Yeah. What did Feynman say?
Break it down.
He says if you can't explain it to a 10-year-old, then you don't know it well enough also. Something along those lines.
But that's my point. If he uses energy density, right? Yeah. Okay, not to be a dick or anything. I'm not saying, hey, define your words or else you lose. Not even with that tone. It's just break it down for me. I'm stupid. Break it down for me. I want to understand what you're saying. I want to have in my head what you have in yours.
Yeah.
And you can't do that with vague terminology. If you ask me to explain how the refrigerator works, and I say the Blorgen moved the jorboard, and you're like,
what is the Blorgen and the jorboard?
Yeah, now you have to break it down.
Then we don't understand, what you're talking about. No, but again, I think that physics,
primitive.
I always say the following. I think this is the best way to put it. Mathematics is for PhDs. Physics is for kids.
Yeah,
if you cannot explain, and I think Einstein and Feynman said it properly there, if you cannot explain it to a 10-year-old, then you have no idea what you're talking about. Okay, you're not doing physics. You might be doing math. You can talk about Einstein's field equations. You can talk about, Niels Bohr and all his equations, and Heisenberg and Schrodinger and whatever. You have no idea what physics is about. If you want to talk to a kid, you got to talk physics. You got to say, look, this is how the farmer pulls on a donkey. You pull with a rope, and everybody will understand. And I can make a movie of that. And if I start saying, look, you need to understand what energy is. You need to understand what mass is. And then you take mass and you push that with so many, here's the equation for it, etc. You lost the guy. The guy can't follow. You say, well, you got to take a course in physics at the university level. And then after all that, they still insist, and they give you the fine print or the closing argument and say, nobody understands quantum mechanics. No kidding. If they don't understand it, certainly I'm not going to understand it. Mother Nature's not going to understand it. You can't explain quantum mechanics to Mother Nature. Period.
I think
we're done.
I think the issue that we're kind of going around are the three kind of forms of communication of math, words, and movies. Where math and words really just kind of convolute me giving you information. If I just show you the movie of what I mean,
right?
I mean, you could misunderstand.
You know, this goes to. I got to interrupt you there because Tom Aggard yesterday said it properly. He said the following. I got to read it over here because I can't see, I don't know why I can't see my image there in the OBS. He says the following. Let's wait for it to come out. It's rational if you can visualize the mechanism. Logic doesn't need to be visualizable. So he says there's a difference between. Yeah, he said that yesterday at the end. He says there's a difference between rational and logic. Okay, he says rational is what you can visualize. I make a movie of my physics theory. I visualize it there on the screen. And I don't need to use a single word. I show you how a car works by showing you the whole movie, a silent movie. We'll bring Charlie Chaplin to do it for us, okay? Logic does not need to be visualizable. Logic, you can say, if A, then B.
That's what we said yesterday.
Yeah, and you can do it with computers. Computer doesn't have to visualize anything. But rational... he's distinguishing rational from logic. That was the issue.
I added one more word because there's a difference between imaginable and rational. This is how I would define it. Imaginable is just any shape that you can have in your head. Okay. Rational is taking something in real life and then making everything that's invisible visible. When you want to explain something, you can't. I mean, yeah, you can visualize an angel. But when you use the superpowers, now how are you going to rationally visualize it? And you can't do that.
And that's one of the issues that I was also going to present an example. You can present a theory involving angels. You can say, look, here's an angel, and you show this human with wings and a little cup on his head, right? A little ring or whatever on his head. Okay, plate or ring. And so now you say, look, here's my theory. My theory is that angels move the earth around the sun. Now I can make a movie of that. I can make a movie of angels moving around the sun. And you say, okay, I understand your theory.
It's imaginable.
It's imaginable because I can put it on the screen. But now let's look at the assumptions, okay? We're going to go, now we go back to assumptions. And we say, okay, hold it. I got a couple problems with it. Why does an angel have wings? I mean, wings on Earth, birds and so on, are because they use them for air. And out there in space, there's no air, so why do they have wings? That's one issue. Another one is, hold it, these guys have superpowers, like, they have so much, they have little mass, because you're a little angel, he's just a human, maybe he's a little bigger, I don't know, and he can push the earth around. Well, where does he get the mass to push the earth around the sun? And so you have questions about the assumption, not about the theory. The theory you can understand. You can say, okay, I see what you're saying. You're saying the angel pushes the earth around the sun. We can all understand the mechanism. We can't understand the assumption, the superpowers, why he has wings, maybe some other issue.
But why? More to that point specifically.
Why his plate is floating around his head.
But specifically, why can't we understand it is because to understand something, there's a key invisible thing that you have to make visible.
Right.
There's some invisible mechanism. There's something that you didn't see.
Make the invisible visible.
Exactly. If you have the car hood closed, you're not going to understand anything.
You got to open up, show the motor.
Open up, show me exactly every single bit that's going on there.
How the gas comes into the engine.
The magician is also good. When he does, why does the magician have the box at all?
Yeah, I mean, he cuts the lady in half. He cuts the lady in half.
The whole point of magic is to not show you
how he does the trick.
Is to hide a part of it so that you go, holy crap, how did he do that?
Is that what Mother Nature does?
Yeah, there's these magicians called Penn and Teller, which they do this one trick with a box where is two magicians, and one guy kind of pops out of this side, he pops out of that side, his feet are over here. Like, how is he doing this? And then after they do the trick, they do the whole thing with
explain it.
Yeah, they do the whole thing with the
open box,
a glass box, where you can see exactly where he's going and where he's putting his feet and where he's putting his hands.
Is that what Mother Nature does?
It's hilarious. No, but that's the point of science.
Yeah, but look, here we have two magnets, right? And Mother Nature is fooling us. She said, look, I can do magic. I can make these things come together from afar. Here it goes. It pulls already, okay? Yeah, and it's holding it, right? And you say, well, how did you do that, Mother Nature? Well, I'm not going to show you the visible parts, the invisible part. I'm not going to make them visible to you. I'm going to let you break your brain to figure out how I did this magic trick.
The whole point of explaining is making something invisible visible. If I say... If a really loud sound happens, right, in the kitchen, and you go, oh, what was that? And I say, oh, I saw it, it was the plate, it fell on the ground. Then you kind of go, okay, in your head you can now visualize the thing that
plate
fell.
Falling down, right.
So now
you say that was a spirit?
Yeah, if you...
Energy?
Yeah, you can't just say... I mean, you have to put some object in the effect of something.
Hopefully,
put it that way.
Hopefully, that's what I'm saying. You got to make there's an object between two magnets, and you got to make that object visible if you want to understand the theory.
Yeah.
If you put nothing there, for sure, no one's going to understand the theory. And if you put a concept there, such as energy, mass, force, whatever you want to put in there, that's a concept, information, love. No one's going to understand your theory.
You have to
for sure.
You have to. There's something invisible that you have to make visible.
Yeah,
that's the bottom line.
And you can't make a concept visible.
But that goes back to what
you can't make a concept visible.
Yeah, you can't make a concept visible. But it kind of goes back to what I was talking about with movies, words, and math, where maybe at physics conferences, everyone should there should be an unspoken rule of complete silence. No one can talk. Anytime
just put it on the board.
Movie, yeah, show us a movie. And then we get the next presenter. He plays his movie.
I got it. I got your idea. That's a good idea. We're not gonna accept blind people, but we're gonna accept deaf.
Only deaf people. Everyone comes with earplugs.
No, you can't hear it. I don't want to hear your explanation. I just want to look at your movie.
Anytime there's an effect.
Yeah, and what are you going to put in each frame? You got to put an object.
But that's my point. Anytime you
what are you going to put, an equation?
Anytime you want to explain a phenomenon.
Yeah.
An effect. Any effect. You hear something, you see something, you feel something. There's some, and you didn't. Okay, let's take out see, because that's the whole point.
Yeah.
If you feel something, hear something, taste something, or smell something, but don't see it, now there's something to explain. Yeah. That's the whole thing. Explaining is literally that visualization where you
magic.
Go, okay,
I'm doing it with magic.
What can I imagine in my head? What's the thing that I put in my head to explain that effect? If something pushes something and I don't see it, okay, how do we explain this? If I smell something, where's that smell coming from? You don't see it, obviously. You're just looking for something invisible to make visible to explain.
I like the current. I like always the curtain. The curtain moves, and your friend says, "Well, the reason the curtain moved is my great grandmother's spirit is in the room, and she moved the curtain." And you say, "Well, maybe if you close the window."
No, but
right?
I mean, extrapolating into anything because, for example,
maybe there's a different explanation.
You can extrapolate to anything that you don't see. For example, if you have a pain in your stomach, right? You feel something, you have an effect,
and you can't see it.
And you can't see it. So what you're trying to do when you're trying to explain it is you're trying to make what's the invisible thing? Obviously I can't see it, but you're trying to imagine it, right? You try to imagine your stomach, and you go,
see it with your brain.
If I put a rock. Like in my head, if in my imagination, if I put a rock in my stomach, right, would it explain this sensation?
Right. So you put a rock, you simulate it with a rock. Yeah. You say, is this causing the pain? Then you say, no, let's try bacteria.
Bacteria, yeah.
So now you put bacteria.
Color it red or whatever.
Right. You say, could this cause the pain? And
but you're essentially trying to make you're never going to see it.
You're simulating with whatever ideas come to your mind. You're trying to explain what's causing the pain.
And explaining is literally making something invisible visible. And not even like literally, just in your head.
Yeah.
Just having something to imagine. If you can imagine it, you understand it.
And with that, we will see you tomorrow at the same time, same station.
And tomorrow our class is just going to be movies. No talking.
Tomorrow we're not going to talk at all. Tomorrow we're just going to
slapstick. Charlie Chaplin up here.
We're going to put Charlie Chaplin silent movies and whatever we find before 1927 when they invented, sound.
Oh, someone has a comment.
Talkies. Oh, okay.
Arthur Wyatt says, someone said this to me when we were talking about magnets. The concept shape comes from visual and tactile perception. The inherently unseeable and untouchable need not have shape.
The inherently unseeable. No. Art. It's not an issue of whether we see or not. We kill all observers in physics. There are no observers. In mathematics, there are observers. In physics, we have no observers. So we don't have to see, we don't have to touch. We have to imagine. We see with our brain. An object, by definition, is that which has shape. So whether I can see it or not, I can't see the air. Here it is again. I can't see the air. But hopefully there's a physical object there. I'm not doing this with magic. Believe me, okay? Please believe me.
Is there such thing as untouchable?
Yeah, they were in the 1950s, the Untouchables.
No, but I mean in physics.
Yeah, I mean,
No, but seriously, there's no such thing as an untouchable thing.
Well, it is if it's beyond. Well, hold it.
It has no effect.
Untouchable is a touchy word.
Oh, we're talking about it tomorrow. But
yeah,
in a nutshell, just off the top of my head, there's no such thing as untouchable. If it's untouchable, it doesn't exist. Kind of thing, where it's like, if it's untouchable, that means it has no effect.
Yeah, the problem with the touchable is that you have to run an experiment to find out if it is touchable. Like the star on the other side of the universe. I can't see it, I can't taste it, I can smell it, I can't do anything with it. Is it touchable? Well, let me run the experiment, I'll tell you.
Yeah.
So it's like you need an experiment.
It's not an experiment thing, I'm just talking about logically. If there's something that's untouchable, right? Assuming we knew for a fact, whatever, we did the experiment and everything. If it's untouchable, what's the point of even talking about it?
Yeah, but hold it. It's a big word because now we have to define what you mean by touch. And we'll get to that tomorrow.
That's a kind of
very big word, especially for the rope model of light and the atom. You need to know what touch means.
Weird.
Because it has to do with the issue of tangling. People ask, well, don't these ropes tangle when they cross each other? And before they tangle, they must touch. Right? Because, it's like, just visualize it for a second. Two ropes coming together, right? First they touch, then they can go through each other or do whatever they want. But first they must touch. So we have to explain touch before we explain tangling. And we'll do that tomorrow. We'll see you then tomorrow, same time, same station. Bye-bye.